So, the next topic in this course is differential equations, and this will be the topic for the next 8 to 10 lectures. Okay. Now, differential equations are seen almost everywhere in chemistry and physics, and you would have encountered them in various areas already. But in this course, what we will do is we will start from the basics of differential equations, and then we will see what are the techniques to solve the differential equations. Okay. Now, a differential equation by definition is an equation that has a derivative of a function in it. So, a differential equation is some equation that has one or higher derivatives and powers of derivatives in it. So, it is like an algebraic equation, but instead of just having variables, you also have derivatives in it. Okay. So, for example, you can have d c by dt is equal to minus k c, where c could be a concentration that changes with time. So, c is a concentration that changes with time. Okay, so, this is an example. Okay. So, this is an algebraic equation where not only is c there, but also c is there, but also derivative of c with respect to time. So, we say that you have c as a function of t, and not only do you have that function, but you also have the derivative of that function appearing. Okay. Now, there are two kinds of differential equations that are commonly encountered. The first is ordinary differential equations, or ordinary differential equations. And we will be using the short notation ODE. Okay, ordinary differential equations, and this should be contrast with what are called as partial differential equations. Okay. So, you have ODEs and PDEs. And these are the two types of differential equations that are commonly encountered. Okay. Now, the only difference between these two is that in an ordinary differential equation, it is the normal derivatives that appear, whereas in a partial differential equation, the partial derivatives appear. So, this is an example of an ordinary differential equation. So, another example is you can have dy by dx 2x dy by dx plus d square y by dx square plus 2y equal to 3 sine x. So, this is an example. This is a differential equation because it is an equation containing y, x and derivatives of y with respect to x, but all the derivatives that appear are the normal derivatives, and so this is called an ordinary differential equation. Whereas a partial differential equation, the classic example is the time dependent Schrodinger equation. You have a d square xt plus you can have let us say half is equal to I by h cross So, this is an example of a partial differential equation. You can have other forms of partial differential equation. Okay. Rather the more typically used one is one where h cross is in the numerator. I h cross. Okay. So, now in this you notice that your psi is a function of x and t, it is a function of both x and t. Okay. So, you have two independent variables x and t, and psi is a dependent variable, and this differential equation involves partial derivative with respect to x and partial derivative with respect to time. So, this is called a partial differential equation. Okay. Now, if in this course we will not be looking explicitly at both kinds of differential equations, we will be mostly working with ordinary differential equations, but occasionally we will refer to partial differential equations. We will see how some of the methods that we are doing are used for partial differential equations. So, we will not be explicitly doing partial differential equations separately from ordinary differential equations. Okay. Next, next we have the concept of the order of a differential equation. And let us restrict all this to ordinary differential equations. So, all that I will be saying in the next in the following lectures will be restricted to ordinary differential equations unless explicitly specified. Okay. So, the order of a differential equation of an ODE is the highest derivative that appears in the ODE. Okay. So, you look at suppose you ask what is the order of this differential equation, the highest derivative that appears is the first derivative. So, this is a first order differential equation, and in this case the highest derivative that appears is the second derivative. So, this is a second order second order differential equation. Okay. So, this is a first order ODE, whereas this is a second order ODE. So, that is what is meant by the order of a differential equation. Okay. Now, next there is a commonly used phrase which is you say a differential equation, a linear differential equation. So, what is a linear differential equation? A linear differential equation is one in which each term has y or differential equation, and let us say for y of x. So, if y is a dependent variable and x is the independent variable, then the differential equation is said to be linear if each term has y or any derivative of y only up to first power. Okay. So, again I will make it explicit. So, if you look at this differential equation, the first term has second derivative of y, okay, but it has only first power. So, you do not have, so and the second term has first derivative of y, third term has just y. Okay. So, if I write that as y double prime plus 2x y prime plus 2y equal to 3 sin x. Okay. So, this is a linear differential equation because each term has a power of y that is only 1 or 0. So, it has only 1 or 0 power of y. Okay. Secondly, so what is an example? So, this would be a linear second order ODE. So, it is linear because it has y only. So, each term has y or derivative of y only up to power 1, and it is second order because the highest derivative that appears is 2. Okay. An example of a nonlinear differential equation is, suppose I had y double prime plus 2x y prime plus 2y square. Now, notice that this term has y square. Okay. So, this becomes nonlinear. Similarly, if I had two y prime. Okay. Now, this term has one y and one y prime. Okay. So, effectively it has y to higher order. So, this is also a nonlinear differential equation. These are nonlinear ODEs. Okay. Okay, so these are the various terminologies that are used. There is one more terminology that is used, and that is called homogeneous differential equation. Okay. Now you can look at this equation. Now, each term has the same power of y. Okay. So, this term has y to first power, this term also has y to first power, this term also has y to first power, this term has no y. Okay. So, a homogeneous equation has each term has same power of y or derivatives. Okay. So, for example, if you had something like y double prime equal to 0. So, each term has one power of y. Okay. So, this is a homogeneous second order ODE. So, this is a homogeneous linear second order ODE. On the other hand, if you had y double prime equal to 3, then this is non-homogeneous it turns out to be linear second order ODE. Okay. So, non-homogeneous linear second order ODE. So, the term that makes it non-homogeneous is this 3, because this does not have any power of y. So, each of these has one power of y, but this does not have any power of y. So, that makes it inhomogeneous. Okay. So far we have looked at various forms that differential equations take, and we have named all of them. Okay. Now, one of the things that you do with a differential equation is to actually solve it, and that will be the main topic of the next few lectures. Before that, I'll talk about what are the various kinds of solutions that you can have to differential equations. Before we go into solutions of differential equations, I want to mention one thing, and this is that in most cases in real scientific research problems, the hardest part is to actually set up the differential equation. Okay. So the process by which you model your system in the form of differential equation is the modeling part. So, when you model your system, and that is when you get your differential equation. Okay. And this is often the hardest part in many scientific research problems, and then once you get the differential equations, you solve it to get the solutions. So, once you get the differential equations, then you have to solve the differential equations, and when you solve the differential equations, you get solutions, and these solutions are of two kinds. Okay, the first is called the general solution, and the second is called the particular solution. Okay. So when you have a differential equation, you solve it, you will get the general solution and the particular solution. Okay. We'll briefly discuss what is meant by general and particular solutions. Before that, I want to say that we already said that modeling your system as a differential equation is often the hardest part in any scientific problem, but once you have the differential equation, then there are various procedures to solve it. Now, in some cases you can actually get a solution in a closed mathematical form. So, this solution can be either analytical. Analytical means you have a mathematical form of solution. Or it can be, in some cases it is not possible to get an analytical solution. You cannot write it in some form of some function, and in those cases you use the numerical solutions. Okay. Where you essentially get the values of the function of the function at various values of the independent variable. Okay. So whenever you are not able to get an analytical solution, you go for the numerical solution, and this is one of the most commonly used techniques in all sciences and engineering. Okay. We'll be in this course we'll be restricting ourselves mostly to the analytical, mostly to those cases where you can write an analytical mathematical solution. Okay. So when you can write this analytical mathematical solution, then we said that there are two kinds of solution. One is called the general solution, and the other is called the particular solution. Okay. So the general solution has a property that it has some undetermined constants. Okay, so it has some undetermined constants. Okay, and these constants are obtained by constants. These are obtained by from boundary conditions. Okay. And a particular solution is after fitting to boundary conditions. So, after fitting to boundary conditions, it has no undetermined constants, no undetermined constants. Okay. So, the general solution will typically have some undetermined constants, whereas the particular solution will have no undetermined constants, and and in order to go from the general solution to the particular solutions, you have to apply the boundary conditions. Okay. So let us take an example. Suppose you take d equal to minus k c. Okay. So this is a differential equation, this is an ODE. Solution c as a function of t is equal to some constant e to the minus k t. Okay. So this k is the same as this k, and you can show that if you take this, if you take the, now if I take this and I substitute in this dc by dt, then I will get dc by dt is minus k times c. Okay, so this satisfies the differential equation for all values of a. So whatever be my value of a, it will satisfy the differential equation, and this is called the general solution. Okay, general solution, and a is the undetermined constant. Now suppose I say that at t equal to 0, c equal to 10. Okay, at t equal to 0, c equal to 10, then you can show that c of t is equal to 10 times e to the minus k t. Okay. Now this is a differential equation. This formula for c satisfies the differential equation. You can show that if I take the derivative of c, I will get exactly minus k times c, but it also satisfies the condition when I put t equal to 0, then this term will go away. So c of 0 equal to 10. So it satisfies both differential equation and boundary conditions, both dE and boundary conditions. Okay, and this is called a particular solution. Okay, so we have a general solution and we have a particular solution, and to go from the general solution to the particular solution, we applied the boundary conditions. Okay, now the question is how many boundary conditions do we need? Okay, how many boundary conditions do we need? In this case, we needed one boundary conditions. Is this, do we always need only one boundary conditions, or are there cases when we need more than one boundary condition? Okay, and the answer is quite straightforward. So if to get particular solution, of nth order ODE, okay, n boundary conditions are needed. Okay. So it is quite straightforward. If you have an nth order differential equation, then you need n boundary conditions in order to get the particular solution. Okay. So if you do not have n boundary conditions, then you cannot get the particular solutions. Okay. So we have the general solution and the particular solution, and now next what we will try to do is to try to actually solve the differential equation. Okay. If you want to specify your problem completely, not only is it important to get the differential equation, but you should also mention the boundary conditions. Okay. So you also need to specify the boundary conditions. So a full-fledged mathematical modeling of your system will involve both a differential equation and the boundary conditions. Okay. So next let us try to look at simple ways of solving differential equations. So now our goal is to find the solution of differential equations. Before we go into that, let me just briefly mention that there are you can have the solution in an explicit form. So if you have a differential equation involving y of x, your solution can be of the form y of x equal to something. This is called an explicit solution, some function of x. So this is explicit solution. Okay. And in some cases it's not possible to separate y and x. It's not possible to write y of x as something. You might have some function of x and y equal to 0, and this is called the implicit solution. So for example, you might have x square plus y square equal to 1, this is an implicit solution. Okay. So, this is some relation between y and x, it is not written as y of x is something. So, this is an example of an implicit solution. Or you can have an explicit solution of the form y is equal to 1 minus x, this is explicit. So, in some cases it turns out that your differential equation, the solution to the differential equation can be expressed as some equation involving x and y. Okay. And in some cases you can separate it into an equation where you have only y on the left and you have x on the right. So, the cases where you can separate it in this form, you call this an explicit solution, in this case you call it an implicit solution. So, it means that y and x are related, but you cannot separate it in this form. Okay. So, now let us go and look at ways to solve. So, to solve differential equations, we will start with first order ODEs. So, a first order ODE means the highest derivative that appears in your equation is 1. So, you cannot have a second derivative appearing in a first order differential equation. Okay. So, how do you go about solving first order differential equation? Now, the first thing you will try to do is what is called as separation of variables. Okay. So, I will illustrate this with an example. Okay. So, for example, if you have x y prime minus 2 x y equal to 0. So, you have a different. So, you have a differential equation of this form. Okay. Now, what you will do is you will say that this is x times dy by dx is equal to 2 x y. Okay. And then what you will say is, or let me make this 2 times, just make it slightly more complicated. You will say 2 by x y equal to 0. So, then you will say is equal to 2 y by x. Okay. Then what you do is you take all the terms involving y to one side and take all the terms involving x to the other. So, you say dy by y is equal to twice dx divided by x square. Okay. And then the next step is to integrate both sides. Now, this involves only y, this involves only x. So, we can carry out these integrals. So, when you integrate both sides, you will get integral x square. So, integral dy by y is natural log of y, okay, and this is twice, this is dx by x square is minus 1 by x, okay, and you can have some constant of integration. So, adding any constant will not change the, if I add any constant, I take a derivative, the derivative of the constant is 0. So, I can always add a constant, and this is your undetermined constant. Okay. So, the solution can be written in this form, and if you want you can write this as y is equal to e raised to c minus 2 by x into e raised to minus 2 by x. Okay. And c is arbitrary. So, e to the c is also arbitrary. So, you can write this as c prime e to the minus 2 by x. So, this is the general solution. So, the general solution has been found, and based on the boundary conditions of the problem, you can get the particular solution. Okay. So, the strategy here was to separate the variables. So, you bring all the terms involving y on one side, all the terms involving x on the other, and once you have done that, you can integrate both sides and you can write the solution. Okay. So, this is the first thing that you try whenever you have a differential equation. Whenever you have any differential equation, first order differential equation, you try to separate the variables. Okay. And in this case, it was fairly straightforward. Okay. Now, in some cases, you can do a change of variables and that can bring the equations to separable form. So, for example, if you have x times y prime equal to x plus y. Okay. So, if you look at this differential equation, then it does not look as though it can be written in separate form. So, if you try to bring the y terms on this side, you will not be able to separate it into terms that involve only x and terms that involve only y. So, this cannot be separated. Okay. So, we cannot separate x and y terms in this case. Okay. So, then what is the strategy to do? And in this case, it turns out that you set u is equal to y by x. Okay. So, suppose I set u equal to y by x, okay, then I immediately I can write u prime is equal to y prime x y prime minus y divided by x square. Okay, so, u prime is this and this is equal to, so okay. So, then that implies x y prime is equal to x square u prime minus y or plus y. So, now if I substitute for x y prime here, what I see is that x square u prime plus y equal to x plus y, cancel the y's. So, I get x square u prime is equal to x. Okay. So, this implies x square du by dx is equal to x, and cancel the x, and what I get is du is equal to dx divided by x. So, I was able to bring it to a separable form. So, this is separable. Okay. So, we started from something that did not look separable. By a simple transformation of variables, we came to a separable form, and once you have separated it, I can easily solve this. So, the solution will be u is equal to natural log of x. Okay. And once I know u, then I substitute for u. So, y is equal to x natural log of x. Okay. So, y is equal to x times natural log of x. So, by transforming variables from y to u, we were able to separate the equations and we were able to solve them. Okay. So, the core of the strategy is to separate the variables, okay, and if you cannot separate it, in a very simple way, you try to transform variables and you try to make it separable. Okay. So, this separation of variables is going to be the core strategy for solving first order differential equations. So, we saw that the first strategy to solve first order differential equations is to separate the variables, and when we are not able to separate it in terms of the variables given, we try to transform the variables, so we can write it in separable form. Now, the question remains, when can we separate variables? Is using transformations. In other words, suppose you are given a differential equation is there a way of knowing just by looking at the differential equation whether there exists a transformation that allows you to separate variables? Okay. So, the question we are asking is it always possible to find a transformation which allows you to separate the variables in your differential equation? Okay. So, here we are really asking about is it always possible to find such a transformation? The answer is no, it is not always possible. In some cases you cannot find a transformation that will allow you to separate variables. And what is the condition for existence of such a transformation? Okay. So, when can we separate variables using transformation? To answer this question, we will write the differential equation in a slightly different form. So, this is a first order differential equation. So, it involves a dy by dx somewhere. So, you have dy by dx is equal to, let me call it some m which is a function of x and y divided by n which is a function of x and y, and just for convenience we will put a minus sign. Okay. So, suppose I can write my differential equation in this form. So, I just express whatever my derivative, this is a function of both x and y. Okay. So, this is also a function of x and y. So, you express your differential equation in this form, then I can rewrite this as m of x y dx plus n of x y dy equal to 0. So, alternatively I can write my differential equation in this form. Okay. Now, when you write a differential equation in this form, now you can ask what is the condition that there exists this transformation that allows you to separate variables, and by writing it in this form we can motivate that such a transformation exists. If there exists a transformation, then this whole left hand side should be equal to, should be an exact differential and should be equal to some du. So, the whole left hand side should equal some differential of some function u of x y. So, it should be an exact differential, and so du is equal to 0. Okay. So, if you believe that you can find a transformation that allows you to separate variables, then the left hand side should be an exact differential, and you should be able to write this, and this implies that the solution is u of x y equal to constant. That will be the solution to the differential equation. So, if this exists, okay, so if separable, then left hand side is an exact differential, okay, and that is du, and du of x y equal to 0 becomes the equation, and this is the solution. Okay, this is if it is separable. And now you go back to your earlier notes on exact differentials, and you will say that if this has to be an exact differential, then dou m by dou y should be equal to dou n by dou x. So, this is the condition for exact, this is the condition that your left hand side is an exact differential. So, once you have this condition, then you know that this is an exact differential. So, therefore, it should be able to separate variables by finding a suitable transformation. Okay. So, this is the condition for existence of such a transformation. Okay. So, now when you are given a differential equation, okay, you write it in this form. Okay. Then you see if derivative of m with respect to y is equal to derivative of n with respect to x. Okay. If that is satisfied, then you know that this is an exact differential. Okay. And once you know that it is an exact differential, then we can go ahead and try to calculate what this u is. Okay. So, suppose dou m by dou y, I am omitting the dependence on x and y, okay, dou x Okay, so I am not bothering to write these, okay, but it is understood that these are functions of x and y. So, suppose you have this condition, then du equal to m dx plus n dy. Okay. This implies partial of u with respect to x equal to m partial of u. In order to solve this, what we will say is that u is equal to integral m is a function of x and y dx. Okay, so, you integrate with respect to x and you have some constant, but this constant is a function of y. So, if you had u written in this form, then you take the partial of u with respect to x, that will give you, this term will give you m, this term will give you 0. So, your partial of u with respect to x will be 1, or you can write u is equal to integral n of x y dy plus some function of x. Okay. So, notice that the constant of integration, when you are doing partial derivatives, the constant of integration depends on the other variable. So, if I have a partial derivative with respect to x, the constant of integration can be any function of y. If I have a partial derivative with respect to y, the constant of integration can be any function of x. Okay. So, this is a strategy for solving this differential equation of first order. So, let us try to take an example. Okay, so, for example, you solve dy by dx equal to minus divided by okay. So, try to solve this differential equation. In order to do this, we immediately notice that m is this. Okay, so, this is m and this is n. Okay, so, that is the first thing we notice. We notice what m and n are. Next, we want to check for this condition. So, check dou m by dou y equal to dou n by dou x. Okay, so check for that, and you can see that dou m by dou y will give me 4 x y plus 1. So 2x into 2y, that is 4 x y plus 1, and in this case dou n by dou x will give me 4 x y plus 1. Okay, so you can show that both of these are equal to 4 x y plus 1. Okay, so this is satisfied. Okay. So, we can see that partial derivative of m with respect to y is equal to partial derivative of n with respect to x. So, we have seen that this differential equation satisfies the conditions of separability. Okay. So, in other words, m dx plus n dy equal to 0, and this is an exact differential. And we call this equal to du. Okay. So, now we have to solve for u. So, we say that partial of u with respect to x should be equal to m is equal to m is 2 x y square plus y plus x cube. So, this is 2 x y square plus y plus x cube. Okay. So, when we integrate this, you will get u is equal to integral 2 x y square plus y plus x cube dx plus a function of y. Okay. So, when I integrate with respect to x, I keep y as a constant. So, this will give me integral x square y, oh sorry, there won't be an integral sign. So, the first term will give me 2x, integral of 2x is x square, y square is a constant. So, constant for integration over x. Second term is y times x. Third term is x cube, integral of x cube is x 4 by 4 plus some function of y. Okay, so, u of x y is this. Now, how do you determine f y? Okay. So, in order to determine f of f y, we use the condition that dou u by dou y has to be equal to n. Okay. And if I take this as my u, then this implies dou u by dou y is 2 x square y plus x. Differential of this with respect to y is 0 plus f prime. So, dou f by dou y is equal to n. N is nothing but 2 x square y plus x plus y. Okay, so now I can cancel this, I can cancel this, I can cancel this, I can cancel this. So, I am left with dou f by dou y equal to y, and this implies f equal to y square by 2. So, we have f equal to y square by 2. So, now we substitute in u of x y. So, we get u of x y is equal to x square y square plus x y plus x 4 by 4 plus y square by 2. Okay. So, we get that u of x y is equal to this. Okay. Now, the differential equation is du equal to 0. So, differential equation is du equal to 0. So, implies solution u equal to constant. So, in other words, the solution can be written as x square y square plus x y plus x 4 by 4 plus y square by 2 equal to constant. So, this is an implicit solution to this differential equation. So, this is an implicit solution to this differential equation. It is a solution because it does not contain any derivatives of y appearing. Okay, so starting from a differential equation like this, we came to this kind of solution, and it is a general solution because it has this constant of integration. And as an exercise, you can verify that this indeed satisfies this differential equation by taking the derivative with respect to x. You take the derivative with respect to x on both sides, then you will get so when I take the derivative with respect to x, then I will have two terms here. So, the first term will be 2 x y square. The second term will be x square into 2 y dy by dx. Okay. This again will have two terms, plus y plus x dy by dx. Okay. This will have only one term, that is x cube. Okay. And the last term will have y dy by dx, and this will be equal to 0 because right hand side has no power of x or no term containing x, and you will get this form. And if you rearrange it, if you take all the terms involving dy by dx and you take all the other terms on the left, you will get exactly this equation. So, you can verify that this satisfies the original differential equation. So, this is indeed a solution of this differential equation. Okay. So, this is always whenever you get a solution to a differential equation, you should substitute back in the original differential equation and see that indeed it satisfies the differential equation. So, this So in other words, I take all the terms involving dy by dx times 2x square y plus x plus y is equal to minus 2xy square plus y plus x cube. Okay. So we came back to this, and we can see that this was indeed the original differential equation that we started with. So what we have here, so this implies this, and therefore this is a solution of this differential equation. Okay. So this is the general strategy for solving first order differential equations. So we try to separate them, and when we are not able to separate them, when we are not able to separate them, we look for exact differentials. Okay. And if this exact differential exists, so if we check that dm by dy is equal to dn by dx, then it is an exact differential, and then we can solve it using this separation of variables. Okay. So the next step is, what happens if a first order differential equation cannot be expressed in terms of this exact differential. So what do you do if you cannot write it in terms of exact differentials? And that's what we will discuss in the next class, and how to go beyond exact differentials.